So in this video, we're going to be talking about how you can prove different things in geometry using coordinates. So like if something's on a coordinate grid, how we can prove different things about triangles and quadrilaterals in particular. To start off with, I want to show you this map, and I know you can't see it very well in the video, but I just got it right off Google Maps. Imagine if we were going to put a cell phone tower in Ringgold. So Ringgold is here. Is it the same distance from Rossville? So here's Ringgold, here's Rossville, and here's Chickamauga. If we put a cell tower in Ringgold, is it the same distance from Rossville as it is from Chickamauga? And we're talking as the crow flies distance, so like directly there, not like on a road or anything. What do you guys think? Is this length, oh, that was not a very good line, sorry. Is that length the same as this length? And how could I prove it? On Google Maps, there's like a little measurement feature where you can actually measure this stuff. I could get out a ruler or a tape measure and physically measure it, or I could form it into a coordinate grid. Coordinate grids are handy because they allow us to come up with like this one unit, makes it like it keeps it consistent all across the map, and so I can use this coordinate grid to find those links. Let's imagine this is 0, 0 right here. And so this would be the point 2, 1, which I listed there for Chickamauga. We've got the point 15, 5 right here for Ringgold, and we've got the point 3, 11 for Rossville. So how could I actually find this distance? Remember, we can't just count. Like, we can't go 1, 2, 3, because that length is a little bit longer than 1 unit. It's close to a unit, but it's a little bit too long. So what I can do is our old handy Pythagorean theorem. You can make this into a right triangle like this, or even like this. And now I can count this stuff, because this is 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so if I do 6 squared plus 12 squared and then square root it, that will give me this length. Go ahead and try that. Go ahead and pause the video and try it for the length to Chickamauga as well, and see if you get the same thing or which one's closer to Ringgold. All right, so hopefully you've tried it. If I make this one into a right triangle, it's 1, 2, 3, 4 by, what was this? 15 minus 2, so 13. If I do 4 squared plus 13 squared and then square root it, that will get me this distance. So type those into your calculator. 6 squared plus 12 squared is 180, and if I square root it, this gets me approximately 13.4. This one gets me approximately 13.6. So actually very close. So it's a little bit further, and again, I was using this point. Maybe you weren't going exactly there in Chickamauga, but from where I have it drawn, it's a little bit further from Ringgold to Chickamauga than it is from Ringgold to Rossville, but just slightly. This is not in miles, this is just in units. So if we wanted, we could break down how much is each unit compared to a mile, but that would be a problem for another day. So you can see coordinate grids can be helpful when we're trying to do problems like this, compare lengths or that kind of thing. If you ever want to show that 2 lengths are congruent, or ever just find a length on a coordinate grid, you have 2 options, and they're basically the same thing. The first one is Pythagorean theorem. Like if I wanted to find the length of this line segment here, I can just make it into a right triangle, because then I can count this side and count this side and use Pythagorean theorem to find the third side. Another option that you have is called the distance formula. This is on your formula sheet. It is on the top left side of your formula sheet, And the distance formula allows you to plug in 2 points and it finds the distance between them. So you plug in x1, y1 would be your first point, and x2, y2 would be your second point, and then you square them both and square root it, and that'll do it for you. That should look pretty familiar to you. For example, x2 minus x1 is basically just finding the length of this side. Like you take x minus x and it finds this length. And then you square it, and that's basically like doing a squared. And then this finds the distance between the y values, which is basically just like counting up how tall it is. And then you square it, which is the same thing as b squared. And then it equals the distance squared. And to solve for it, you square root both sides, and so that's why this is square rooted. And so basically it's literally the same as Pythagorean theorem. It's like the x value squared plus the y distance squared, and then you square root it. So sometimes proving things on a coordinate grid is very easy. Like for example, see these two rectangles here, I want to prove they're congruent. To prove they're congruent, I just need to show that literally everything's the same. And so to do that, I don't even need Pythagorean theorem here. I could just count the sides. See how this side length here is 1, 2, 3, 4, 5? And this is 2. This is a 2 by 5 rectangle. This one is also 2 by 1, 2, 3, 4, 5. And they have 90-degree angles. So that's it. All the sides are congruent, all the angles are congruent. By doing those calculations, I proved those rectangles are congruent. However, sometimes the rectangles or shapes aren't like directly on the lines. Sometimes they're a little harder to see. For example, prove that this is a parallelogram. That might be a little trickier. Let's graph it real quick. 2, negative 1, 1, 3, 1, 2, 3, 4, 5, 6, 5, and 7, 1. So it's this shape right here. And I want to prove it's a parallelogram. How am I going to prove that exactly? So that's kind of one of our goals for today. We're going to come back to this in a second. And here's another example of problems that we might want to answer. Quadrilateral ABCD has these points. What is its most specific name? For example, is it a parallelogram, or is it more than that? Is it a rectangle or a rhombus, or even a square? So, and how can I tell? So this is the kind of thing we're going to get into. All right, first let's talk triangles, then we'll get into quadrilaterals. Just a reminder, with triangles, you've got scalene, which have no congruent sides, also no congruent angles. Isosceles, which have 2 congruent sides and 2 congruent angles. I remember that because it's got, I was going to say 2 S's, but it's got 3. And 2 congruent angles. And then equilateral has 3 congruent sides and 3 congruent angles. That one's easier to remember. All right, if I want to prove whether or not this is an isosceles triangle, it's going to have 2 congruent sides. So I'm going to need to find the lengths of the sides. One way I could do this is get out a ruler or a tape measure and literally measure the sides, but I don't actually have to do that because I can just do some calculations and use the grid to help me out, and I won't have to measure it. So I'm going to go ahead and find the length of all 3 sides. Remember, you can do this with Pythagorean theorem, like you could make it into a right triangle. Or you can do distance formula. I'll show you both. This right here is a right triangle. It's got 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8. So it's 4 squared plus 8 squared, and then I'll square root it. That will give me this length here, which is 4 squared plus 8 squared is 80. So I'm just going to leave this as the square root of 80. That's what this side is. We could break that down or get a decimal, but I'm just going to leave it. For this other side, This one right here I could make into a right triangle as well, even though it's a very narrow right triangle. It's a triangle that is base of 1, a height of 1, 2, 3, 4, 5, 6, 7, 8. It's pretty clearly not the same as that triangle because it was 4 by 8, this is 1 by 8, but it might be the same as this one, so we'll go ahead and do 1 squared plus 8 squared and then square root it. 1 squared plus 8 squared is 65, and so this side right here is the square root of 65. Okay, so far it's not isosceles, but if this one matches either of those, then it will be isosceles. Let's do this one actually with the distance formula, just so you can see that. The distance formula says do the square root of x2 minus x1. So 2 minus negative 5, and then you square it, and then you do y2 minus y1, and square that. So that would be 2 plus 5, or 7 squared, plus negative 4 squared, which is 65. So the square root of 65. So notice, this was the square root of 80, this was the square root of 65, and this was the square root of 65. So is it isosceles? Yes. And my proof is literally this work. It's because AC is congruent to BC, and I proved it by showing they were both equal to the square root of 65. So that's why we call this proof with coordinates, because you're literally proving things by doing stuff on a coordinate grid. Okay, let's jump into quadrilaterals here. I want to refresh you on a few things about quadrilaterals. First of all, if you're going to prove that something's a parallelogram, all you have to do is show that the opposite sides are parallel. I know there are a lot more properties that have to do with parallelograms, but this is by definition all that it is, just parallel sides. A trapezoid, if you remember, is just one pair of parallel sides, usually not two. A rectangle is a parallelogram, remember that. In addition, it's got all congruent angles. They're all 90 degrees. This means that if you take a look at each of these sides, they should be perpendicular. Like these two sides should also be perpendicular, and these two sides should be perpendicular, and these two sides should be perpendicular. So keep that in mind. For a rhombus, remember a rhombus is also a parallelogram. All four sides are congruent. So this is almost like proving an equilateral triangle. You would just find the length of all the sides and show if they're the same or not. A square, remember, is all of the above. It's a rhombus, all four sides are congruent. It is a rectangle, all the angles are 90, and it's a parallelogram. The opposite sides are parallel. So first of all, we've talked about how to tell if lengths are the same, but what about the whole parallel side thing? So how can we tell that these two sides are parallel? This one's pretty easy. They're both kind of right on that grid line. They both have a slope of 0, and so these two are very clearly parallel. But what about these two sides? How can I tell they're parallel? The way I can tell is because they are sloped the same. Remember, two lines are parallel if they have the same slope. Literally, they're sloped the same. Notice this one has a slope of 1, 2, 3, 4 over 1. And this one also has a slope of 4 over 1. Notice I'm not finding the lengths. I'm not doing Pythagorean theorem or anything. I'm finding the slope. The slope tells me these aren't parallel to each other. Yes, they are congruent, but that's not what I'm doing here. Same thing here. If I were to look at the slopes, you see how this one has a slope of down 1, 2, 3, 4, and over 1, 2, 3, 4, 5, 6, 7, 8. So negative 4 over 8, or negative 1/2. This one I think is the same, down 1, 2, 3, 4, over 1, 2, 3, 4, 5, 6, 7, 8. So it's also got the same slope. That tells me that PA is parallel to LR. Same thing with these. This one goes down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and over 2. So negative 11 over 2. And this one I believe is also negative 11 over 2. So PL and AR are also parallel. That's all you need to prove that something's a parallelogram. Find that the two sides are parallel by showing the slopes are the same. All right, now let's talk about perpendicular lines. So we've got parallel. What about perpendicular? Remember, perpendicular means they form a 90-degree angle with each other. So I'm going to go ahead and tell you these two lines are perpendicular. What do you notice about their slopes? Go ahead and pause the video and try to find their slopes and see what you notice. So hopefully you've tried it. This blue one has a slope of negative 1, 2, 3 over 1, 2, 3, 4, 5, 6, negative 3 over 6, or you may have noticed down 1 over 2, it simplifies to negative 1/2. This red one has a slope of up 2 over 1, up 2 over 1, up 2 over 1, so 2 over 1, or 2. What do you notice about these two slopes? We've got negative 1/2 and 2 over 1. So this will always happen. When two lines are perpendicular, their slopes are what we call opposite reciprocals. This means, first of all, if one is positive, the other's negative. That's because if this one's going up, this one's got to be coming down. And they're always flipped of each other. That's what the word reciprocal means. It means you flip the fraction. So if this one is 2 over 1, this one's 1 over 2, and vice versa. And if this one's negative, that one's positive. So they're opposite and reciprocal. So here is kind of a summary of all of that. If you want to prove or verify these shapes on a coordinate grid, you really only have two things that you might do. One is find lengths. We do that with the distance formula or Pythagorean theorem. That would show that things are congruent. The only other thing you could really do is find slopes. Slopes would tell you if two lines are parallel, or they would tell you that two lines are perpendicular, which would help with the whole rectangle thing because they have perpendicular sides. So let's go through a few examples here. Let's go back to that one we had earlier. I want to prove that this is a parallelogram. So I've got 2, negative 1, that's point A. I've got 1, 3, that's point B. I've got 1, 2, 3, 4, 5, 6, 5, that's C, and 7, 1. So I want to prove this is a parallelogram. Okay, to prove it's a parallelogram, I know that a parallelogram has congruent sides, but that's not its definition. Its definition is that it has parallel sides. So to prove this, I'm going to prove, are these two parallel and are these two parallel? How do I prove two lines are parallel? Remember, that's not the lengths, that's their slopes. So the slope of BC is up 2 over 1, 2, 3, 4, 5. So I'm going to say these are the slopes. For BC, it's 2/5. For, what is that? Oh, it's A. For AD, it's also 2 over 5. And so that tells me that BC is parallel to AD. I also know that AB right here, you go down 1, 2, 3, 4 over 1. So for BA, it's negative 4 over 1, or negative 4. For this one, it's also negative 4 over 1. And so that tells me that those are parallel. So BA or AB is parallel to CD, and this is my proof. This proves that it's a parallelogram. Just have a seat and get your stuff out. All right, one more example here. I want to know what quadrilateral this is. So if I graph it, I've got -3, 0. That's point A. I've got 3, 2. That's point B. I've got 4, -1. That's point C. And then I've got point D, which is -2, -3. All right, it's pretty clear this is not a square. I think we can just rule that one out just by our common sense here. Is that right? Okay. It may not even be a parallelogram. It might just be, it might just be a quadrilateral. And so the first thing I'm going to want to do, it'll just be like 5 minutes, sorry. The first thing I want to do is make sure it's at least a parallelogram, because if it's not a parallelogram, it can't be any of the others. So let's find the slopes. The slope of AB is up 2 over 1, 2, 3, 4, 5, 6. So the slope of AB is 2/6 or 1/3. Let's make sure this one's the same. Up 2 over 1, 2, 3, 4, 5, 6. Okay. So DC is the same, also 1/3. Those are parallel, that's good. These are parallel. For AD, it's down 1, 2, 3 over 1. So down 3 over 1. And for BC, it's also down 3 over 1. Or -3. So these two are parallel. So it's definitely a parallelogram. It might also be a rectangle or a rhombus, probably not a square, but it could be one of those two. To be a rectangle, remember, I've got to have 90-degree angles, which means these have to be perpendicular. And remember, the way we tell if they're perpendicular is, are the slopes opposite reciprocals? So like, compare the slope of AB and BC, these two right here. Do you see how this one is positive 1/3 and this one's -3 over 1? Those slopes are opposite reciprocals. You flip it and make it negative. And so these two are the same, opposite reciprocals. And so this is actually a rectangle. I've got 90-degree angles because I know all of these are perpendicular to each other. It's pretty clear this is not a rhombus because these two are definitely not congruent. But if I wanted to prove that, I could find the lengths of these sides. For example, BC, if we made that into a triangle, it would be a 1/3 triangle. So 1 squared plus 3 squared, and then square root it. For DC, it would be 1, 2, 3, 4, 5, 6 by 2. So 6 squared plus 2 squared. And if you compare those, they are definitely not equal to each other. So it's not a rhombus or a square. It is, however, a rectangle. And also a parallelogram, also a quadrilateral. The most specific name is what it asked for, meaning what we're going to go with here is rectangle because that's like as specific as we can get. Rectangle implies that it is also a parallelogram, also a quadrilateral. So just to sum this up, I know that seems like a lot, but you really only have two options you can do. Finding lengths, which would prove various things are congruent, or finding slopes, which would prove sides are either parallel or perpendicular. And that pretty much wraps it up. Ooh, that was